Today, welcome back to the A-Level Physics course by Tamias Dekas. I hope you enjoyed the previous lessons. Today, we continue talking about physical quantities and units, and the aspect we will focus on today is SI base and derived units. By the end of today's lesson, you will be able to recall SI base units. You already studied them in the IGCSE physics course. We are going to remind ourselves with them briefly and talk about the significance of their usage. Also, you will be able to express derived units in terms of SI base units. We will be looking at the mathematics behind that expressions and solve some example problems to understand the process completely. Now, imagine yourself driving a car, and once in a sudden, you see this road sign that tells you you have to move with the speed less or equal to 50. You apply the brakes of the car immediately and decrease the speed of your motion to allowed value. However, you are stopped by a police officer who tells you, "Sir, with all the regrets, I have to conclude that you are driving too fast." "No," you apply immediately. "I was driving with 60. As I've seen the sign, I decreased the speed of my motion to 50. "I understand, sir," says the officer, "but you are driving Chevrolet Tahoe, designed in the United States. Your speedometer has a scale of miles per hour, indicated over here, while in our country, the road signs are indicating the speed in kilometers per hour. Unfortunately, you are driving too fast." This imaginary situation might have caused a lot of trouble in real life. However, mostly the modern cars are equipped by a speedometer with a double scale, such as the one shown in the figure. The same confusion might happen among people of different nations joined in a group as they try to communicate with each other. Hence, a person from Spain will speak Spanish, from Italy, Italian, from Gulf, Arabic, etc. One way to avoid such confusion is to have a common language of communication. For example, English can be chosen. The same is done by the scientists worldwide. They use the same units that scientific community has made an agreement upon. The idea of using common units takes its origin in 1792, just after the Great French Revolution has ended. Hence, abbreviation SI stands for a French phrase Système International, introduced much later in 1957. SI base units are the fundamental units used by scientists worldwide. There are 7 of them. For the unit of mass, kilogram; for the unit of length, meter; for the unit of time, second; for the unit of electric current, ampere; for the unit of absolute, also known as thermodynamic temperature, Kelvin; for the unit of amount of substance, mole; and for the unit of luminous intensity, candela. All the other units can be expressed with the help of corresponding equations in terms of SI base units. For example, the equation of motion is given in the form of Newton's second law of motion. Acceleration of motion is directly proportional to the resultant force acting on the body and inversely proportional to the mass of the body. Acceleration is the rate of change in velocity. Thus, the unit of acceleration is meter times second to the power of -2. Mass is measured in kilograms. So, if we rewrite the formula in the following way, it is easy to see that the unit of force, Newton, can be expressed in terms of SI base units of mass and acceleration. It means that Newton is a derived unit. Every physical quantity can be expressed through SI units, such as examples shown here. As you can see, some of the derived units include base unit as well, such as the unit of latent heat of fusion, joule times kilogram to the power of -1. Here, joule is a derived unit, while kilogram is a base unit. Also, we can express this unit only in terms of SI base units. If we express joule in terms of kilogram multiplied meter square times second to the power of -2, we will obtain the unit of latent heat of fusion in terms of base units. After replacing the joule in the equation with the corresponding base units and making some mathematics, we can see that kilogram cancel each other out, and so we are left with meter squared times second to the power of -2. Although you are not likely to see the unit of latent heat of fusion in the books written in this form, it is very useful to practice experiencing derived units in terms of base units, as this is a very common question in the A-level exam. Now it's a time to practice expressing derived units in terms of SI base units. The task is to express the following derived units in terms of SI base units: Hertz, dioptry, Pascal, Coulomb, and Watt. Pause the video, solve it by yourself, and then play the video back again to check your solutions. I'm going to give you some hints, following which it's going to be much easier to do the task. Firstly, we need to identify the physical quantity that has the following derived unit. Pay attention that the same unit can refer to different quantities. For example, meter can be unit of length, height, distance traveled, etc. The point to notice here is the quantities must be of the same nature, such as in the example given. So you will need to choose among those quantities according to the situation explained in the problem. Secondly, you need to remind yourself with the equation or formula that corresponds to this quantity. Next, repeat step number 2 unless you have all the quantities represented by SI base units. Last but not least, make proper mathematics. Hertz is the unit of frequency. In order to express it in terms of SI base units, we need to write an equation for the frequency. Thus, we can have the expression if we look at the definition of frequency. Frequency is amount of complete revolutions in a given amount of time. Number does not have a unit, while time has the base unit of second. Hence, Hertz is equivalent to second to the power of -1. Sometimes it is also pronounced as inverse of second. Dioptry is the unit of optical power. Optical power is the degree by which any optical system converges or diverges the light. It is an inverse of focal length of the optical system. Focal length is measured in meters. Hence, dioptry is equivalent to inverse of meter, or meter to the power of -1. Pascal is the unit of pressure. Any formulae for the pressure you can remember are useful to express Pascal in terms of base units. In particular, we are going to use the formula for hydrostatic pressure. P equals rho multiplied G multiplied H. Density has the unit of kilogram per cubic meter, Acceleration due to gravity is measured in meters per second squared, and height is measured in meters. Overall, after combining the units into the equation of hydrostatic pressure, we can see that Pascal is equivalent to the product of kilogram times inverse of meter times second to the power of -2. Coulomb is the unit of electric charge. Electric current flowing through the wire is the rate of change of charge over the cross-sectional area of the wire. We can express the charge as the product of current and the time. The unit of electric current is ampere, the unit of time is second. Hence, Coulomb is equivalent to the product of ampere and second. Watt is the unit of power. Power is the rate of performing work in the system. Work done by the force is the product of that force to the distance over which the object has been moved and the cosine of the angle between these two vectors. The force, according to the Newton's second law, is the product of body's mass and the acceleration of the motion caused by the force. All the quantities in here are represented with SI base units. Hence, Watt is equivalent to the product of kilogram times meter squared times second to the power of -3. That's it for today. Thanks for watching this video. If you liked it, press the like button, subscribe to my channel for more A-level physics videos if you haven't done it already. Here with you was Tamias Dekas. Check out the description below this video to find out more about me. See you next time.